Okay, let's look at some review questions for Chapter 10. Here's question number 1. Stellar parallax is used to measure the, stellar parallax or trigonometric parallax is just that measurement along the baseline of the star against the backdrop of stars. So it's used to measure the distance to that star using geometry. Parallax can be used to measure distances to stars accurately to about 200 parsecs, or multiply that by 3.25, 650 light years. Question 2. The angle of stellar parallax for a star gets larger as the angle gets larger as the star gets closer. Is that one of our answers? Distance to the star increases? No. It would be a distance to the star decreases. B. Size of the star increases? No. It would have nothing to do with the size. C. Size of the telescope? No. Length of the baseline increases? Yes. If we had a larger baseline, then we'd get a greater angle as we're looking at the star with respect to the backdrop. So the angle of the stellar parallax would increase with the length of the baseline. Astronomers typically make observations 6 months apart using the diameter of the Earth's orbit, which would be 2 astronomical units. Question 3. You can best model the size and distance relationship of our sun, and the next nearest star, which would be Proxima Centauri, using, the one I like to use is say that the Earth and the sun were a meter apart, then the next nearest star, Proxima Centauri, would be down in Montgomery, which would be 270,000 meters away, or 270 kilometers away. What can we do to be similar to that? A tennis ball and one on the moon. Now that's too far away. 2 beach balls separated by 100 city blocks. That's too close. 2 grains of sand 100 light years apart, way too far away. 2 golf balls 100 kilometers apart. That's about right. Think about that. 2 golf balls 100 kilometers apart, that's about the order of what I was talking about. 2 baseballs 100 yards apart, too close. So we're here at number D. The sun is 1 million miles in diameter. Next nearest star is about 25 million times further away. So we better study our own sun. Question number 4. A star's proper motion is the proper motion is the amount of motion the star will make over the course of a year as measured on the same day each year. So you just want to make sure you make the same measurement, see how far it's moved against a backdrop of stars on that same day each year. So that would be its annual apparent motion across the sky. Barnard's star has the most annual apparent motion, its proper motion, on the same day each year. Question 5. In the stellar magnitude system invented by Hipparchus, a smaller magnitude indicates the absolute magnitude is what we're talking about. And a smaller magnitude, or even in the apparent magnitude, a smaller magnitude means it's brighter, because class 1 were the brightest stars, class 6 were the dimmer stars. So the smaller the magnitude, the brighter the star was. Question 6. A star's apparent magnitude is a number used to describe how our eyes measure how it appears in brightness to us. So how our eyes measure its brightness as we see it. Not its absolute luminosity, because as we see it, that's what it appears to us, and it's not necessarily its absolute brightness. Question number 7. The absolute magnitude of stars is brightness as seen from a distance of, Well, the absolute magnitude is taking a standard distance away from us and putting all the stars at that standard distance, measuring its brightness at that distance. So we have a way to compare all stars. And that is at a standard distance of 10 parsecs away, or about 33 light years. And our answer here then would be 10 parsecs, or D. Question 8. Which of the following quantities do you need in order to calculate a star's luminosity? Well, we need to know how it appears to us, its actual brightness as it appears, and then we need to know how far away it is and what its temperature is. So, let's see, we need to know its apparent brightness and the distance to the star. Those would definitely be what we need to know so we can calculate its true brightness. I guess the temperature could go into calculating its brightness. So we need to know A and D for sure. Question 9. What are the two most important intrinsic properties for classifying stars? Well, in the HR diagram are those two properties. On the vertical axis we have luminosity, or absolute brightness. And on the horizontal axis we have temperature, or spectral class. So let's see. How are they classified here? We have luminosity and surface temperature. That would do it. Luminosity on the vertical, surface temperature on the horizontal. That's it. HR diagram plots stars based on luminosity and surface temperatures. Or you could say absolute magnitude and spectral class. Question 10. Vienne's law tells us that the hotter an object, the peak wavelength of its emitted light. The hotter the object, the bluer it gets, and the cooler, the redder it gets. And as we go bluer, we get to a shorter wavelength, higher frequency. Cooler is a longer wavelength, lower frequency. So the hotter the object, the bluer or shorter the wavelength. Question 11. We estimate the surface temperature of a star by using, well, there's several ways we can estimate the surface temperature of a star. One is through Vienne's law, as we just stated. The other one is to look at its actual color. I mean, if we look at Betelgeuse, it's a red star. If we look at Rigel, it's a blue star. The actual color will tell us its surface temperature. The pattern of absorption lines in the spectrum will tell us, if we see a predominance of hydrogen, let's say class A, that could tell us its temperature. Or if we don't see hydrogen, we just see helium, spectroscopic helium that has been devoid of its electrons, ionized helium, that's what I was trying to say, then that would tell us a type O star. Or if we see molecular atoms, then it might be a type M star. So the pattern would tell us as well. Difference in brightness through red and blue filters could set up a black body diagram, which would tell us the temperature. So all these things could be used to determine the temperature of a star. All of the above. Question 12. Which spectral classification type corresponds to a star like the Sun? Well, our Sun is a nice average star. It's meant for general consumption, so it is a class G star. Actually, the G comes from its spectral class based on its hydrogen spectrum. Question 13. The key difference between the spectra of B stars and G stars is, well, B stars would have a more prominent hydrogen spectrum. That's the way it originally was set up. So B stars show strong hydrogen lines, G stars show weaker hydrogen lines. That's true. Let's look at B. B stars show few metal lines. G stars show many. That's not true. Neither one shows any metal lines. C. B stars have no metal atoms. G stars have no hydrogen atoms. Neither one is true. So only true one is A. B shows stronger hydrogen lines than G, because that's the way the A, B, C, D, E, F, G was first set up. Question 14. Astronomers can estimate the size of a star using, well, we can get the size of a star if we know its the distance to the star and its temperature and apparent brightness. So we can determine its actual brightness. So we need to know A, B, C in order to determine the size of the star. Brightness and temperature are used to plot the star on the HR diagram, indicate its approximate size, and then if we know its distance, then we can figure out its total size. Question number 15. Eclipsing binary stars are very useful for determining the eclipsing binary can tell us the relative size of the stars. And if we measure the period of that revolution, we can ultimately determine the mass of the stars. So they're very useful for determining the mass of the stars. Question 16. What is the single most important characteristic in determining the course of a star's evolution? Well, in an HR diagram, as you go on the main sequence, you go to greater mass, and the mass will tell you whether you're going to have a blue giant or a red dwarf or a star like the sun, yellow in the middle. And as they're less mass, then they're going to burn their hydrogen over a much longer time, and they'll survive for a very long time, like the red dwarfs. So the mass will tell us how long it's going to last on the main sequence and how soon it's going to go through the life cycle of its whole star life cycle. So in determining the course of a star's evolution, mass is the key most important component. It'll determine how fast it forms, its luminosity on the main sequence, how long it will shine, and ultimately how it's going to go from there for the rest of its lifetime. That concludes this short quiz on Chapter 10. Hope you enjoyed it.